I'm Sagacious, CRS. Welcome to this video on open wounds. Let's begin. In this video, we shall derive an equation for the mean analogous damage inflicted per second against a single target X by open wounds within some time tau, given some probability P to trigger open wounds on hit and some time T bar between hits. We shall explore the following in future videos: relations between monster health regeneration and open wounds, stacking separate instances of open wounds, optimization, and much, much more. The reason that optimization is going to come last is that it's going to depend on what we're trying to optimize. Are we trying to optimize for canceling monster health regeneration? That probability may be different from optimization pertaining to damage. Are we trying to optimize cumulative damage between multiple targets in which we're stacking instances of open wounds? Or are we singling out only a single target? For these and a repository of other reasons, optimization will come last and will likely consist of a series of if-then contingencies. This video should be divided into the following sections: the introduction, which is currently ongoing, a summary, the derivation, and then examples. Timestamps are below in the description of this video, so feel free to jump ahead if you're so inclined. Some remarks. Let me know if you'd like me to provide you with an Excel sheet to automate the calculations. For additional content, please like and subscribe. I stream on Twitch. I stream Fridays, Saturdays, and Sundays from 7:30 p.m. to 10:30 p.m. Mountain Time. If you're on the East Coast, just add 2 hours to that. My Twitch channel is linked to this YouTube channel. You just have to go to the About Me section, and the link is there. If you don't know any of those time zones that I mentioned, you can check on the Twitch channel my schedule, and it will tell you my schedule in your time zone. With all of that said, let's proceed to the summary. So some constraints that we are assuming. One and only one target X is being attacked for all times T less than or equal to tau. And I'll say what tau is in a second. All hits are assumed to occur within time tau, where tau is greater than 0 and less than or equal to 8 seconds, where 8 seconds is the duration of open wounds. The reason that we have set 8 seconds as the upper bound, that is the duration of open wounds, is because it simplifies the preliminary equation, as we don't have to account for instances in which open wounds expires. However, such instances will be included in future videos, so rest assured. My intention is to lay a foundation of simple equations from which we can make inferences in the future. We are not alternating targets. We are not alternating weapons either. Now, to be clear, we are assuming no alternation of targets or weapons for a repository of reasons. We assume no alternation of weapons because we don't want the probability to trigger open wounds to vary, nor do we want the damage inflicted per hit to vary as well. Having said that, there may be instances in which the alternation of weapons does not contradict these factors. In such instances, this equation may be applicable. However, to be super careful, it is probably better to avoid such instances unless you know what you're doing, in order to mitigate inaccuracies. We are assuming that the target X is not initially afflicted with open wounds. So at time T equals 0 and for all times less than 0, the target is not afflicted with open wounds. So to put this more succinctly and intuitively, this equation is intended to model situations like this. So here we have a character and some monster. The time tau is given above, and right now we're at T equals 0. Now at T equals 0, the attack sequence begins. We have our first hit, and let's just suppose, for the sake of simplicity, that this hit triggers open wounds, right? And so now open wounds begins to accrue damage. So as we pull back, another hit, open wounds continues to accrue damage. We pull back, another hit, open wounds still accrues damage. We won't be able to fit another hit in this attack sequence because the upper bound of time tau will not allow that given our attack frequency. However, open wounds will still accrue damage in this instance, as demonstrated below. So this is essentially what we're thinking. We're attacking one and only one target. All hits are assumed to be within time tau, and the target, of course, is assumed not to be suffering from open wounds at time T equals 0 and for all times less than 0. Okay, so here's our equation. Given an applicable sequence of consecutive hits made against a single target X in time tau, it follows the analogous expected damage per second inflicted by open wounds against target X in time tau, which will denote d sub O of pt bar bar is given by this formula. And of course, you can see I emphasized in bold applicable. I think I've done a pretty good job of motivating what I intend applicable to mean, where P in the interval 0 exclusive, 1 inclusive is the probability to trigger open wounds. Note that this equation is not defined for P equals 0, which is fine because, we don't have to worry about that. If P is 0, then you're not getting any damage from open wounds. Where R sub O is the damage per unit time in seconds inflicted by open wounds. So this is what you would look up on an applicable website, right? That scales with level. That's what R sub O is. Where T bar in the interval 0 exclusive tau inclusive is the mean time between hits in seconds. Note that this is the reciprocal of hit frequency. So for example, if you're hitting 5 times per second, the reciprocal of that would be 1 in 5, so 0.2 seconds between hits. It's worth noting that T bar could also be conceptualized rather than simply applying to the time between hits in a continuous attack sequence when we're just hitting constantly, you know what I'm saying? It could also be the time between maybe I hit, I go and do something, I come back, I hit again, right? The only constraint is that T bar has an upper bound that is 8 seconds. So T bar is less than or equal to tau, and tau's upper bound is 8 seconds for this equation to be applicable. So this equation potentially has more generality than simply, constraining it only to instances in which we're thinking of continuous attack sequences. Another thing worth noting is while the probability to hit doesn't directly appear in this equation, it is implicitly there. That is to say, given n hits that occur in some time tau, if there's some probability that any of those n hits land, then there exists a corresponding T bar, that is time between hits given that probability, that is the expected T bar. So in other words, given a chance to hit, we can adjust T bar accordingly. So that implicitly shows up in this equation. However, in future videos, I will include it just to be extra careful. Lastly, we have the following lower and upper bounds for the analogous expected damage per second inflicted by open wounds against target X in time tau. In other words, it's greater than or equal to 0, and it's less than or equal to R sub O times 1 minus T bar divided by tau. If you want to know how I got those lower and upper bounds, feel free to watch the rest of the video. Some other things to note. You'll notice in this equation that it includes the floor function. That is, we take the floor of tau divided by T bar. The floor function operates on a real number as an input, and the result of the floor function, that is the output, is the greatest integer less than or equal to that real number. So for example, if I divide tau and T bar, and let's say I get 3.2 or something like that, then the floor is the greatest integer less than or equal to 3.2, which will be 3. So intuitively, the floor function just gets rid of the decimal part of that real number, giving you only an integer as a result in the output. So that's how you'd calculate these, indicated in red. Now, notationally, while the analogous expected damage per second inflicted by open wounds against target X in time tau depends also on tau and R sub O, usually we think of these things over sufficiently small intervals of time as constant. That is, my character's level doesn't change that quickly, so usually the damage I'm doing based on level R sub O is more or less constant, and we usually have a pretty good idea of the window of time in which we are attacking, right? So we think of tau and R sub O as fixed, and so really it's P and T bar that may vary. And even T bar you could argue is fixed, so really this could just be a function of P. However, you may want to adjust T bar and P accordingly, because remember, T bar is the time between hits, which may not necessarily be the same as the time between hits for a continuous attack sequence. Maybe you land a hit, you take some reprieve and go and do something else, you come back and get another hit, right? That's why I've left T bar as a variable as well. That's more of a notational thing. Let's look at a graph of this. So the vertical axis is some value of the expected analogous damage inflicted by open wounds against target X in time tau. So if we have a value of 0, that means in that time tau we did 0 expected damage per unit time over that interval of time tau. The horizontal axis measures values of T bar, so these are the reciprocal of hit frequency. In other words, the time between hits. The horizontal purple line is R sub O. That's the value you would look up on an applicable website that scales with level, right? It's what most people usually approximate the damage per second they do. The blue curves are upper and lower bounds respectively for various values of P. So P equal 1 is the upper bound. It is the maximum damage we will do. The lower bound is P equals 0.01 because in Diablo 2 Resurrected, there's really no smaller unit of probability than 1%. The red is some value of P greater than or equal to 0.01 and less than or equal to 1. So let's see how this changes with varying values of P. The blue curves are the upper and lower bound respectively for varying values of P. The black horizontal line is R sub O. The red curve will vary for P greater than or equal to 0.01, less than or equal to 1. So let's see how this curve varies as we let P vary over this interval, that is from 0.01 to 1 inclusive. So there's the lower bound, there's the upper bound. Okay. Now you can graph d sub O of P T bar bar with respect to probability, meaning you let probability be on the x-axis rather than T bar. And if you do that, you will observe that diminishing returns set in. However, the precise way in which diminishing returns set in will vary. It will depend on the relationship between P, T bar, and tau. If we started to solve for ideal values of P in which we avoid diminishing returns, etc., that's going to veer into the territory of optimization. So I think it wise for us to hold off on that. There are a repository of other variables to include to better inform our optimization. In addition to that, it will depend on what we are trying to optimize, right? So for those reasons, we're going to hold off on optimization, and I've excluded a graph of this with respect to probability. So that's coming in future videos. Okay, let's use this equation in an example. So suppose that R sub O is 1.2 damage per second, that a character hits a target 3 times in 8 seconds such that the time between each hit is 2.5 seconds, and that said character has a 2 in 3 chance to trigger open wounds per hit. This will result in the following table. If you're curious of how exactly I came up with this table, feel free to watch the rest of the video. All you need to know is that this will result in a mean cumulative amount of 5.24 damage. So that's the cumulative damage we would expect that we dealt over this period of 8 seconds. So if we inflicted an expected cumulative damage of 5.24 repeated over a period of 8 seconds, then the analogous expected damage per second inflicted by open wounds against target X in time tau equal 8 seconds would be given by this amount divided by 8, which is 0.65 repeated. So if our equation is correct, then we must have that d sub O of 2/3, 2.5 bar, is equal to 0.65 repeated when we choose tau equal 8 and R sub O equal 1.2. So let's see if that's the case. There's our equation. We plug these values in, and sure enough, that is our result. So that saves us a lot of tedium. That's great. Now, you'll be pleased to know that you can add the analogous expected damage per second from this equation inflicted by open wounds against target X in time tau to existing damage per second as long as there are no obvious conflicts. However, care must be taken when doing this. Let me explain. And we'll do this with an example. Suppose that R sub O in this example is 16 damage per second, that a character who inflicts 1 to 3 damage per hit hits a target 2 times in 4 seconds, such that the time between each hit is 1.75 seconds, and that said character has a 1 in 2 chance to trigger open wounds on any particular hit. Notice that this example differs from the last example in that we are including the damage inflicted by the character per hit, right? Last example was only the damage from open wounds. Let's see what happens. So this results in the following table. Again, if you want to know how I came up with this table, just watch the rest of the video or go to the example section. So this results in a mean cumulative damage of 24. So if we inflicted an expected cumulative damage of 24 over a period of 4 seconds, then the analogous expected damage per second inflicted against target X in time tau equal 4 seconds is given by 24 over 4, or 6 damage per second. Okay. What was the analogous expected damage inflicted by said character from hits, right? Meaning the 1 to 3 damage per hit to target X per second in time tau equal 4 seconds. This is kind of counterintuitive and most people would incorrectly calculate this. I'll get to why in a second. But if we look at our table, the mean cumulative damage we did after these 2 hits is 4. Okay, so given that the character inflicted an expected cumulative damage of 4 hits in time tau equal 4 seconds, it follows that the expected damage per second from hits is given by 4 over 4, so 1 damage per second. Thus, if our equation is correct, we must have that d sub o of 1/2 1.75 bar is 5 damage per second when tau is 4 and r sub o is 16. So let's use our equation. Let's plug in these values, and sure enough, we get 5 damage per second. And of course, observe that if we add this to the correct calculation of damage per second from hits, we get 6 damage. So that's good. Okay, so notice that if we had computed the expected damage per hit, so, 1 plus 3 over 2 is 2, and multiplied that by the mean hit rate, so 1 over t bar, which is 1 over 1.75, or 0.571428 repeated, then we would have actually overestimated the analogous expected damage inflicted per second within time tau equal 4 seconds, right? Because if we did that multiplication, we'd get 1.142857, or that's the repeated part of the decimal, plus 5, which would be 6 point, and all of that additional amount is actually an overestimation. Let me explain why, okay? If we've performed some portion of an attack animation, but that attack has yet to land, then all of that damage, we don't multiply by that fraction. It hasn't occurred yet, so it's actually 0. The only sense in which it makes sense to include that fractional part is if tau is unbounded. That is, if you're thinking of, unbounded periods of time over which you're doing this attack animation. So this is a common way in which people incorrectly overestimate for finite periods of time the damage per unit time they do over that interval of time. In other words, succinctly, as tau approaches infinity, that's when this idealized mean, in other words, the mean times the reciprocal of t bar, that's when that's more accurate to use. So if t bar in the interval 0 tau is the mean time between hits in seconds for some character, and mu is the expected damage inflicted by said character to some target X per hit, right? That's like what you would calculate in a D2 damage calculator. Then the more accurate approximation of analogous expected damage inflicted by said character from hits to target X per second in time tau is actually given by mu over tau times the floor of tau over t bar. Thus, to reduce inaccuracies, as this example showed, you should add the analogous expected damage per second from this equation inflicted by open wounds against target X in time tau to mu over tau times the floor of tau over t bar instead. So indeed, if we do that, we see that this sum is equal to, well, we just showed that this portion in red is just 5, right? And sure enough, the average of that is going to be 2. 2/4 is 1/2. The floor of 4 divided by 1.75 is 2. Cancellation of 2's. 5 plus 1 is 6. So indeed, this does work. And it gives us the following equation. Given an applicable sequence of consecutive hits made against a single target X in time tau, it follows that the analogous expected damage per second inflicted to target X in time tau is given by this equation, where P in the interval 0 exclusive, 1 inclusive is the probability to trigger open wounds. R sub O is the damage per unit time in seconds inflicted by open wounds, what you would look up on applicable websites that scales with level. T bar in the interval 0 exclusive, tau inclusive is the mean time between hits in seconds. And mu is the expected damage inflicted to target X per hit, right? That's what you would calculate for melee damage on a D2 damage calculator. And remember, tau is greater than 0 and less than or equal to 8 seconds, where 8 seconds is the duration of open wounds. For all times tau in excess of 8 seconds, this equation is not applicable. That will conclude the summary. So now let us proceed to the derivation. Now, as I said previously, these are some constraints that we are assuming for this equation. We're assuming that one and only one target X is attacked for all times t less than or equal to tau. We're assuming that all hits delivered occur within time tau, where tau is greater than 0 seconds and less than or equal to 8 seconds, where 8 seconds is the duration of open wounds. So for all hit sequences greater than 8 seconds, this equation is not applicable for reasons that should become clear throughout the derivation. The primary reason for which I've made this constraint is in the interest of simplicity, as if we account for times tau greater than 8 seconds, we have to include instances in which open wounds expires. I have an equation for the damage in such instances. However, I want to build on simpler equations in future videos, in which those and other topics will be addressed. We are assuming no alternation of targets. We are also assuming no alternation of weapons. This is done in the interest of mitigating the chance that maybe our odds of triggering open wounds vary between hits, or the mean damage inflicted by a particular weapon varies, etc., etc. It's worth noting, however, that there may be instances in which alternation of weapons allows for these things to be constant, and in such instances, this equation may be applicable. However, in the interest of being conservative, it's probably wise just to not use this equation in those instances unless you know what you're doing. We're also assuming that the target X is not initially affected with open wounds. So open wounds has not been applied at t equals 0 over all times less than 0. Okay? In other words, more succinctly, this equation is intended to model situations like this. So the attack sequence begins at time t equals 0. And here our character scores a hit. Let's just say for this counterfactual hypothetical that this particular hit triggers open wounds. So it's going to begin accruing damage. And so there's another hit and it continues to accrue damage. There's another hit. Now there's insufficient time for another hit to be scored within time tau up there, right? So be that as it might, open wounds will still accrue damage over this remaining time, as it does. So that's essentially the situation that this equation is trying to model. Okay, let tau be an R positive and let it be a period of time such that it's less than or equal to 8 seconds, where 8 seconds is the duration of open wounds. Again, we are only thinking about attacking a single target over a period of time that is less than or equal to 8 seconds, but not 0. Suppose that a sequence of n consecutive hits, H1, H2, HK, Hn, are made against a single target X in time tau. So here's an illustration. There's the bar indicating the time tau in question. Hit 1 is delivered. Hit 2 is delivered. Hit 3 is delivered. And hit 4 is delivered. Note that we are assuming a continuous attack sequence, such that all attacks are made with the same weapon. So we're not alternating weapons against a single target X in time tau. At least one reason for this assumption is that we want the probability to trigger open wounds to be constant, as well as the mean damage per hit to be constant, etc., etc. In instances in which alternation of weapons does not change the damage per hit, the chance to trigger open wounds on hit, or the time between hits, etc., we can relax these constraints. However, in the interest of being super careful, it's safer, if and when applying this equation, to not apply it to instances in which weapons are being alternated. For any kth hit, H sub k, let T sub k be a value greater than 0, that is a real number, in other words, an R positive, be the mean time at which H sub k occurs, such that we have these sequence of times, T1 greater than 0, T2 bigger than T1, onward and onward, with T sub n, the time at which the last hit in the sequence occurs, being less than or equal to time tau. So here's a representation graphically. At time t equals 0, we begin attacking. At the time of the first hit, T sub 1, we see that it's bigger than 0. There's some time between that hit and the next hit occurs at time t sub 2. Again, time t sub 3 is the time at which the third hit occurs, and t sub 4 is the time at which the fourth hit occurs. And we see that t sub 4 satisfies that it is bigger than 0, but it is less than or equal to tau. It should be noted that t sub k is an R positive for all k and z positive, such that 1 is less than or equal to k less than or equal to n. In other words, k is the index moving between 1 and n, given a sequence of n hits, and t sub k is strictly positive for all of them. This implies that time t equals 0 marks the time at which we begin attacking the target. We are not defining t equal to 0 to be the time at which the first hit is delivered. That's an important concession, and something to keep in mind when considering the applicability of this equation. So for any kth hit, where k is in z positive and k is less than or equal to n, let's define t sub k tilde to be a value in R positive such that t sub k tilde is equal to t sub k minus 1 if k is bigger than 1, or simply t sub k when k is equal to 1. Remember, t sub k is just the time at which the kth hit occurs. So here's a representation. At time t equals 0, the attack sequence begins. At time t1, we have, by definition above, t sub 1 tilde. Some time passes, the second hit is delivered, and at time t sub 2, the time at which the second hit is delivered, we have t sub 2 tilde. Some time passes, and at the time t sub 3, or the third hit is delivered, we have t sub 3 tilde. Time passes, and at the time of the fourth hit, t sub 4, we have t sub 4 tilde. We can think of t sub k tilde as the time between the kth hit and the k minus 1th hit for all k bigger than 1. Why bigger than 1? Well, at k equal 1, there's no between hits, right? Moving on, let t bar be a value in R positive, in other words, a real number bigger than 0, such that for all positive integers n, it has the following definition. T bar satisfies that it is the sum of t1 tilde plus t2 tilde plus t3 tilde, onward and onward, all the way up to t sub n tilde, divided by n. Observe that, given this definition, t bar is equal to the sum of t sub k tildes for all k varying from 1 to n, as shown here, divided by n. Let's expand this expression using the definition of t sub k tilde for all k from 1 to n. For k equal 1, t sub k tilde is just t sub k. In other words, t sub 1 is t sub 1 tilde. However, for k greater than 1, we see that t sub 2 tilde is equal to t sub 2 minus t sub 1, right? That is the time of the kth hit minus the time of the k minus 1th hit. Similarly, t sub 3 tilde is t sub 3 minus t sub 2, and so on, until eventually t sub n tilde is t sub n minus t sub n minus 1, and all of this is divided by n. Now, t sub 1 is equal to t sub 1 minus 0. So let's just express that. Doing this, we observe an interesting pattern. Notice that the first term in each set of parentheses is canceled by the second term in the next set of parentheses. So t1 cancels with negative t1. t2 cancels with negative t2. t3 cancels with negative t3, etc., until tn minus 1 cancels with negative tn minus 1. Obviously, tn minus 2 will be canceled earlier in the sum, leaving only t sub n and 0. Of course, 0 is just 0, so really it leaves only t sub n. Thus, it follows, given the definition for all positive integers n, that t bar is equal to t sub n divided by n. Given the definition that t bar is equal to tn divided by n for all positive integers n, it follows that we can think of t bar as the mean time required to carry out a particular hit. It is important to note that if and when we think of t-bar as constant, which we'll be doing hereafter, we are not necessarily assuming that the time between any two hits is constant itself, but that the mean time between any two hits is constant. This is an important distinction. For example, consider this diagram. We have the time interval tau, in which 4 hits are carried out. At time t sub 4, we have t bar as a constant. However, observe that t sub k tilde can vary for k less than or equal to n in a myriad of ways to satisfy that t bar is constant. Now, it's also worth noting that letting t bar be constant is analogous to simply assuming that the time between any particular hit is the same. In other words, that there's no variance in attack animation as well. So it is at our discretion as to which we prefer. I mention this only to emphasize that the generality of these equations is broader than simply the assumption of no variance in attack animation. Given the definition of t bar equal to t sub n divided by n for all positive integers n, it follows that by multiplying both sides of the aforementioned equation by n, we can show that n times t bar is equal to t sub n for all positive integers n, by definition of t bar. Therefore, it follows that t sub k equals k t bar for all n equal k and z positive. That is, t sub 1 equals 1 times t bar. T sub 2 equals 2 times t bar, etc. T sub k equals k times t bar, and t sub n equals n times t bar. Now remember, this is saying that we are choosing n to be a particular value of k. And also worth noting, we are assuming t bar itself to be constant hereafter. Another way to interpret t1 equal to 1 t bar when t is constant is to imagine that t1 varies, that is the time at which the first hit varies, such that t bar is constant. That is, that the expected time for t1, the time at which the first hit lands, is t bar. Here's a visual aid. Here we have variable t sub 1 tildes, analogous to times at which the first hit lands. Observe that these average 2 t bar. So t1 varies such that the expected time for t1 is t bar. Similarly, another way to interpret t sub 2 equal to 2 t bar when t bar is constant is to imagine that t sub 2 varies such that t bar is constant. That is, that the expected time for t sub 2 is 2 t bar. A visual aid is given below. Here we have t2 varying such that the expected time for t2, the time which the second hit lands, is 2 t bar. More generally, another way to interpret t sub k equal to k t bar when t bar is constant is to imagine that t sub k varies such that t bar is constant. That is, that the expected value for t sub k is k t bar. This also implies that t sub k tilde is equal to t bar for all k and z positive. For if k is bigger than 1, given the definition of t sub k tilde, we have that t sub k tilde equals t sub k minus t sub k minus 1. Applying this principle, t sub k tilde is equal to k t bar minus k minus 1 t bar. Distributing, we have k t bar minus k t bar plus t bar. Observe that the k t bar minus k t bar cancel. Thus, t sub k tilde is equal to t bar for all k and z positive. If k is 1, then by definition, t sub k tilde is just t sub k. And for k equal 1, t sub k is t sub 1, which is 1 t bar, just t bar. I recommend taking some time to ruminate on the diagram I showed you earlier, just to make sure we understand what we're saying here. Moving forward, note that because we are assuming that the target was not already suffering from open wounds at time t less than or equal to 0, and the character must hit target X in order to apply open wounds. It follows that open wounds can only accrue damage during the time remaining after the first hit is delivered, within time tau. That is, tau minus t sub 1, the time at which the first hit occurs, which is equal to tau minus t bar, under these assumptions. Here's an example. The first hit lands at time t sub 1, which, per our assumption, is equal to t bar. The soonest that open wounds can trigger under these assumptions is on the first hit, at time t equal t1 equal t bar seconds. Now, once this happens, open wounds can accrue, and so it begins for some time greater than t bar, it continues until it is accrued for time t equal tau minus t bar. Now, it's worth making the concession that this is an approximation. That may not be exactly frame perfect. However, for our purposes, this will be a reasonable approximation. This will also be a case in which the greatest damage possible will be done, which we will address later. Let R sub O be a positive real number such that it is the rate per unit time in seconds at which open wounds damages target X. So this is what you would look up online, right? At max roll or whatever. It's the part that scales based on character level. For any kth hit, H sub k, where k is in Z positive, and k is less than n, if open wounds first triggers on hit k, then the cumulative damage inflicted by open wounds until the next hit in the sequence is given by R sub O times T sub k plus 1 tilde. By definition, T sub k plus 1 tilde is T sub k plus 1 minus T sub k. So it's important to understand what we're saying here. We're saying the rate R sub O is going to be applied for this amount of time, T sub k plus 1 tilde, which is just the difference between the k plus in time, between the kth plus 1 hit and the kth hit. Applying our previously established principle, T sub k plus 1 is just k plus 1 times t bar, and T sub k is k times t bar. Distributing, we have that R sub O times k t bar plus t bar minus k t bar follows. Observe that the k t bar and negative k t bar cancel, leaving only R sub O t bar. This makes sense, as per our previous assumptions, t bar is defined as the mean time between hits, so R sub O will be applied for this duration. This will be true for all k, but I'll use the k equal 1, the first hit, as an example. Open wounds triggers on the first hit at time t equal t1 seconds. R sub O accrues for t equal t bar seconds, resulting in a total amount of R sub O times t bar. This will be true for any kth hit and kth plus 1 hit. Thus, given a sequence of n and z positive consecutive hits, h1, h2, hk, hn, made against a single target x in time tau, it follows that for any kth hit h sub k, such that k is in z positive and less than n, if open wounds first triggers on hit k, then the cumulative damage inflicted by open wounds between hits, so this is between all hits, against target x in time tau, is given by R sub O times T sub k plus 1 tilde, plus R sub O times T sub k plus 2 tilde, onward and onward, up until we have R sub O times T sub n tilde. Let's factor out R sub O to simplify the expression. We just established that T sub k tilde is equal to T bar for all k and z positive. So under these assumptions, we have that R sub O times a summation of T bar n minus k times is equivalent to this. Remember, it triggered on hit k, and so there are n minus k terms. Thus, it follows, factoring out T bar, that we have R sub O times T bar times n minus k. Here's a visual aid. Open wounds triggers on the first hit, so k equal 1, at time t equal t1 seconds. it begins to accrue. There's the damage that accrues between the first and second hit. There's the damage that accrues between the second and third hit. And there's the damage that accrues between the third and fourth hit. If we add these up, how many are there? There are 3 multiples of R sub O times T bar. And per our equation above, n minus k is 4 minus 1, which is 3. So this comports with our intuition. Observe that if it had instead triggered on hit 2, we would have 4 minus 2, we would have only 2 stacks. So this makes sense. Okay. So if it first triggers on some hit, what cumulative damage within the time t sub n, that is the time at which the nth hit occurs, can we expect? If k equals 1, then setting k equal to 1, we have R sub O T bar times n minus 1. That makes sense. For k equal 2, we simply subtract 2, and so forth. At present, this equation is defined such that k is strictly less than n. However, suppose that k equals n. If k equals n, then R sub O T bar times n minus n is just 0. The case when k equals n makes sense, as R sub O times n minus n T bar equals 0 because there is no remaining time over which R sub O can apply damage in time tau between hits, as all hits have already been dealt to the target X. As a result, we can remove the restriction for this equation that k is strictly less than n. So let's do that. Now this equation is sensible for all k less than or equal to n. We showed earlier that for any kth hit h sub k, such that k is in z positive and less than n, if open wounds first triggers on hit k, then the damage inflicted by open wounds between hits k and k plus 1 is given by R naught T bar. Thus, R naught T bar is the mean damage inflicted by open wounds between hits against target X. For given n minus k applicable hits, assuming it triggered on the kth hit, and that there are n hits in total, we observe that R sub O T bar times n minus k, the cumulative amount, divided by the number of terms n minus k is R sub O T bar. So let D sub O be an R positive, in other words, a strictly positive real number, and let it be the mean damage inflicted by open wounds between hits against target X such that D sub O is defined to be equal to R sub O times T bar. The reasons for this simplification will be clear shortly. Then, R sub O T bar times n minus k equals D sub O times n minus k. We can simplify then and think of stacks of D sub O, that is, stacks of the mean damage inflicted between hits. So let's substitute. Okay. Moving on. You might have noticed that we define the value above to be the cumulative damage inflicted by open wounds between hits against target X in time tau, rather than simply the cumulative damage inflicted by open wounds against target X in time tau. Why the distinction? Recall that T sub n is defined to be allowed to be less than or equal to tau for all n and z positive. Observe that if T sub n equals tau, then the equation above is the cumulative damage over time tau. Here's a picture. To say T sub n, in this case the time at which the final hit, so in this picture the fourth hit occurs, is equal to the time tau, is to say that there's no time remaining for any damage to have been dealt. We would have, in this instance, 3 stacks of R naught T bar, which is just D sub O, so 3 instances of D sub O. It would be correct to say this is the cumulative damage inflicted within this period of time by open wounds. However, if T sub n is less than tau, then the equation above is not the cumulative damage over time tau. Consider. So here we have all of the accrued damage between hits, but now let time continue to pass after the time at which the fourth hit has occurred. So time passes. And now at time tau, the current equation does not account for this damage, only the damage accrued thus far between hits. Thus, the cumulative damage inflicted by open wounds against target X in time tau has two components to consider. The cumulative damage inflicted by open wounds between hits, which we previously defined, and the cumulative damage inflicted by open wounds after all hits. Together, these sum to the total damage delivered to the target within time tau. So suppose that t sub n is less than tau. What does this mean? Again, it means that the time at which the nth hit is delivered is less than the time interval tau. Then it follows that tau minus t sub n is greater than 0. Observe that in this case, tau minus t sub n must be less than t bar, as to assume tau minus t sub n is greater than or equal to t bar would contradict our assumption that only n hits were delivered to the target X within time tau. Here's a picture to explain. So here we have 4 hits delivered, and only 4 hits. Here we have the time needed for n plus 1 hits, in other words 5 hits, is greater than the time that remains. That's what we're saying. We're saying that tau minus t sub n, assuming only n hits, must be less than t bar for this to make sense. Given that t sub n equals nt bar, as we previously established, for all n and z positive, it follows that tau minus t sub n equals tau minus nt bar for all n and z positive. During this time interval, tau minus nt bar, we can infer that there is perhaps enough time for some portion of an attack animation to play out, but insufficient time for another hit to be scored. Hence, tau minus t sub n is less than t bar. Be that as it might, open wounds will still accrue damage over this time, if it was triggered at all, that is on any of the n hits in question. So, back to our visual analog. I chose n equal 4 arbitrarily. This would follow for any of the others. But suppose open wounds triggers on hit 4. Then R sub O accrues for time tau minus t sub n seconds, resulting in the cumulative remaining damage accrued. Thus, given a sequence of n and z positive consecutive hits, h1, h2, hk, hn, made against a single target X in time tau, it follows that for any kth hit h sub k, such that k is in z positive and k is less than or equal to n, if open wounds first triggers on hit k, then the cumulative damage inflicted by open wounds after all hits have been made against target X in time tau is given by R sub O times tau minus t sub n, as we just showed in the previous slide. Simplifying, R sub O times tau minus nt bar, per our assumptions. Remember, this is the equation for the cumulative damage inflicted by open wounds after all hits. Now that we've defined the cumulative damage between hits and after all hits, we need only put these two things together. So let's do that. Thus, given a sequence of n and z positive consecutive hits, h1, h2, hk, hn, made against a single target X in time tau, it follows that for any kth hit h sub k, such that k is in z positive and k is less than or equal to n, if open wounds first triggers on hit k, then open wounds will accrue damage at rate R sub O over time tau minus t sub k. Pictorially, we mean this. I've chosen k equal 2, that is the second hit, to be the triggering hit for arbitrarily. Any kth hit choice that is applicable will suffice. So open wounds triggers on hit k, and R sub O accrues for time tau minus t sub k seconds. Inflicting cumulatively R sub O times tau minus t sub 2, or more generally, times tau minus t sub k. Okay, implying that the cumulative damage inflicted by open wounds against target X in time tau is algebraically given by R sub O times tau minus T sub K, which is equal, because T sub N is less than tau, to the following: R sub O times tau minus T sub N plus T sub N minus T sub K. Observe that the red part is equivalent to simply adding 0, so nothing has changed. However, reordering these terms, we see that this is equal to T sub N minus T sub K plus tau minus T sub N. Simplifying by distributing R sub O, we see that R sub O times tau minus T sub K is equal to R sub O times T sub N minus T sub K plus R sub O times tau minus T sub N. We observe that R sub O times tau minus T sub K is equal to R sub O times N T bar minus K T bar plus R sub O times tau minus N T bar. Let's factor out a common factor from the left of T bar. And recall by definition that D sub O is equal to the product R sub O times T bar. So we see that the cumulative damage can be expressed as the sum of the cumulative damage accrued between hits and the cumulative damage accrued after all hits. Going back to our visual analog, we had established that R sub O would accrue for a period of time tau minus T sub 2. We can simply split this, as we did algebraically previously. That is, this is equivalent to R sub O times T sub 4 minus T sub 2. Plus R sub O times tau minus T sub 4. Applying our definitions pertaining to T bar and N, and then factoring out a T bar on the left-hand side, and simplifying to D sub O, we see that this comports with our equation above. The damage to the left is the damage accrued between hits, and the damage to the right is the damage accrued after all hits. Here we see that N equal 4 and K equal 2. There have been 4 and only 4 hits in total delivered, and open wounds is triggered for K equal 2. Although we could simplify this formula further, we're going to leave it in its present form for reasons that should become clear later on in the derivation. Notice that if T sub N equals tau, that is the time at which the nth hit is given, equals tau, then N T bar equals tau, implying that this sum is equal to D sub O times N minus K plus R sub O times tau minus tau. But tau minus tau is 0. And so R sub O times 0 is just 0. And so this sum, that is the cumulative damage, is just D sub O times N minus K, which makes sense, as there is no time after all hits have been delivered for open wounds to accrue damage. Thus, all of the damage, that is, the entirety of it, will derive from damage accrued between hits in time tau. Thus, there is fortunately no need for us to break this into a case of 2 different formulas, depending on whether or not T sub N equals tau or T sub N is less than tau. This satisfies both. So let's look at a few scenarios. So on the left-hand side, we're going to see when open wounds first triggers, and then we'll see what this formula produces for cumulative damage in time tau. If K equals 1, then the damage accrued between hits is going to be D sub O times N minus 1, right? That many multiples of D sub O, where D sub O is the damage between hits. There will be N minus 1 D sub O's, which makes perfect sense, assuming it was triggered on the first hit, plus whatever amount of time remains after the nth hit occurs. Tau minus N T bar will be the time over which R sub O accrues. So that makes sense. Just so, at K equal 2, we get similarly meaningful results. And so on. Observe that K equal N, we will have no damage accrued between hits. This makes sense. No matter what N is, if we have only N hits in the sequence, and open wounds triggers only on hit N, then there's no part of that damage between hits that's going to accrue. The only portion will be after all hits. So this makes sense thus far. Now, if T sub n equals tau for the equation above, then R sub O times tau minus NT bar equals R sub O times NT bar minus NT bar, implying that R sub O is really being multiplied by 0. So it's 0. In other words, the second component will be 0 as expected when T sub n equals tau. So for our table, under those conditions, we would observe that when open wounds first triggers on a particular hit, the cumulative damage within time tau on the right would be, for k equals 1, d sub O times n minus 1. In other words, if there's no time after the nth hit for any additional damage to accrue, the only damage we'd have is n minus 1 stacks of d sub O, the damage between hits. For k equal 2, we also have expected results. And for k equal n, we have 0. This makes perfect sense. If k equals n is the hit that triggers open wounds, and n is the last hit in the sequence, there are no additional hits that can accrue damage between hits. Furthermore, our assumption under these conditions is that T sub n equals tau, which means there's also no remaining time over which open wounds can accrue for this period of time tau. Hence, cumulatively, we would have 0 damage. In other words, this would be the instance in which literally our last hit is the hit that triggers open wounds at exactly time tau. There's no time remaining to accrue damage after all hits, and there are no more between hits applicable to accrue damage between hits. Okay, now we're going to make some notational changes as we incorporate probability. Let alpha sub n of k be defined as d sub O times n minus k. In other words, alpha sub n of k is going to be the component accrued cumulatively from between hits. Beta sub n will be defined as R sub O times tau minus NT bar. So beta sub n can be conceptualized as the component accrued from after all hits. Then it follows, given what we've established thus far, that for all kn and z positive, such that k is less than or equal to n, that this sum, d sub O times n minus k plus R sub O times tau minus NT bar is equal to alpha sub n of k plus beta sub n. This is a notational change for brevity as we incorporate probability. Observe that n, R sub O, t bar, and tau are usually known once we fix them, right? We usually know for how long we're attacking, more or less. We usually know the mean time between hits that we will deliver. We usually have a pretty good idea of what R sub O is based on our character level. And we usually know, given t bar and tau, how many attacks will be occurring. Implying that only k is usually unknown. That is, we do not usually know on which kth hit, if any, open wounds will be triggered once we fix n, R sub O, t bar, and tau. This will be important moving forward. For all k, n, and z positive, such that k is less than or equal to n, as previously stated, we have that the cumulative damage is given by alpha sub n of k plus beta sub n. While beta sub n only depends on n, alpha sub n of k still varies once we fix n for k less than or equal to n. Here's a visual diagram to understand. Here is alpha sub 4 of 1. Remember, this is the cumulative damage accrued from between hits, so alpha sub 4 of 1 means that we have hit only 4 times, and this is the instance in which open wound triggers on the first hit. What if it triggers only on the second hit? We would do less damage. Alpha sub 4 of 2 would be another case, but observe that beta sub 4 is the same. Alpha sub 4 of 3 would be if it only triggered on the third hit. Again, beta sub 4 is the same. And lastly, alpha sub 4 of 4 would mean 0, right? If it triggers on the last hit, there are no more hits to be accrued. There's no damage to be accrued between hits. All of our damage, as previously established, will come from beta sub 4. That is R sub 0 times tau minus 4t bar, the time remaining after the fourth hit in this visual analog. That's what we mean by this. Okay. So let's consider the total hits we have, n, and the possibilities of alpha sub n of k, as well as the possibilities for beta sub n. If we've delivered only one hit in total, then there's only one value for k to range over, right? Alpha sub 1 of 1 is the only case. In other words, do we or do we not trigger open wounds on hit 1? And there's only one possibility for beta sub n, that's beta sub 1. If we do 2 hits, again, beta will not vary, it's beta sub 2. However, the damage accrued from between hits cumulatively will vary depending on whether it's triggered on hit 1 or hit 2. So we have alpha sub 2 of 1, alpha sub 2 of 2. For n equal 3, we see that alpha sub 3 of 1, alpha sub 3 of 2, and alpha sub 3 of 3 are all possibilities. That is, the cumulative damage accrued from between hits can vary depending on whether we trigger on the first hit, the second hit, or the third hit. Whereas beta only varies based on whether we trigger it at all. That's why it doesn't vary, right? So we just have beta sub 3. Continuing, for any general positive integer n, we have alpha sub n of 1, alpha sub n of 2, alpha sub n of 3, alpha sub n of n, and only beta sub n to consider as possibilities. One way to think of this is that for the damage accrued between hits, there are, assuming n hits, n possible instances in which open wounds first triggers. Remember, we are assuming open wounds is not active for any time t less than or equal to 0. Therefore, for it to be applied, it must trigger on a particular hit. Thus, for all n and z positive, there are exactly n cases of alpha n sub k, but only one case of beta sub n. Each variant of alpha n sub k is a case in which open wounds first triggers on hit k, for k and z positive, such that k is less than or equal to n. Thus, for all n and z positive, there will be n plus 1 cases. N cases of alpha n sub k, and 1 case of beta sub n. Thus, for all n and z positive, there will be n plus 1 probabilities. Technically twice these numbers, but you'll see why that's not so important in a minute, so just bear with me. N probabilities, 1 for each case of alpha sub n of k. That is how likely any of these are to occur, right? N of them. And 1 probability for beta sub n. So let p sub alpha sub n of k be a real number in the interval 0, 1 inclusive, and let it be the probability that alpha sub n of k occurs for all k, n, and z positive. Let p sub beta sub n be a real number in the interval 0, 1 inclusive, such that it is the probability that beta sub n occurs for all k, n, and z positive. Then for all k, n, and z positive, such that k is less than or equal to 1, then beta sub n times p sub beta sub n plus 0 times 1 minus p sub beta sub n is just equal to beta sub n times p sub beta sub n. In other words, when I said previously that there were 2 technical cases, that's because given a probability something occurs, there's 1 minus that probability that it does not. We're multiplying it by 0 in the case it doesn't occur because that's essentially the damage we'd have if it didn't trigger. I'm just showing you that the sum of when it does trigger and when it doesn't can be simplified to this. Hence, while there are technically 2 cases, as far as we're concerned, there's only 1 case. In the same light, alpha sub n of 1 times the probability that alpha sub n of 1 occurs plus 0, what happens if it doesn't occur, times the probability it doesn't, is just alpha sub n of 1 times the probability that alpha sub n of 1 occurs. The same for alpha sub n of 2, all the way down to alpha sub n of n. So a way to think of this is that we're taking alpha sub n of k for all k less than or equal to n, and we're weighting it according to the probability it occurs. So one way to think of this, stepping back from all this abstraction, very simply, is that we're taking each case in which open wounds triggers on a particular hit, and looking at the cumulative damage accrued between hits in that case and weighting it with the probability based on the likelihood that it does occur. We are summing that together and weighting those things accordingly to account for all possible instances over which open wounds can first trigger to get an expected value. Same thing for beta. Okay, given what I just showed you in the previous slide, we're not going to include in this equation instances in which it doesn't occur because that's just 0 and it just goes away, right? So given a sequence of n and z positive consecutive hits, h1, h2, hk, hn, made against a single target x in time tau, it follows that the expected cumulative damage inflicted by open wounds against target x in time tau, which we'll denote d sub o sub n, is given by d sub o sub n equal to alpha n of 1 times the probability alpha n of 1 occurs, plus alpha sub n of 2 times the probability that alpha sub n of 2 occurs, and so on, added all the way up until alpha sub n of n times the probability that alpha sub n of n occurs, plus beta sub n times the probability that beta sub n occurs. Let's rewrite this in summation notation for succinctness. And so we see that d sub o sub n is equal to the summation as k varies from 1 to n inclusive of alpha sub n of k times p sub alpha sub n of k plus beta sub n times p sub beta sub n. Now, for reasons that will become clear later, we're going to let p be a real number between 0 and 1, but not 0 or 1, and we'll let it be the probability that any kth hit made against target x in time tau triggers open wounds. Note that this is not the same as either of the probabilities discussed above. This is simply the probability that open wounds triggers for any kth hit. In other words, this would be what's on your item. Some percent chance p of open wounds. Note that we are assuming that p is constant for all hits k and z positive, such that k is less than or equal to n hereafter. Now, as I said previously, it's worth noting that in instances in which weapon alternation doesn't change the percent chance, you may get away with using the following equation in such instances. However, to be super conservative, we're going to restrict our analysis to instances in which there is no alternation of weapons. All right, so let's apply this equation starting at n equal 1. Suppose that we hit only n equal 1 time within the interval of time tau against a single target. Then the expected cumulative damage inflicted by open wounds against target x in time tau is given by, let's use our formula. D sub O of 1, following this formula, is the summation as k varies from 1 to 1 of alpha sub 1 of k times p sub alpha sub 1 of k, plus beta sub 1 times p sub beta sub 1. Okay, let's evaluate the summation. That's going to be alpha sub 1 of 1 times p sub alpha of 1. Looking at alpha sub 1 of 1, let's apply the definition. Remember, this is the portion of damage accrued cumulatively from between hits. So alpha sub 1 of 1 is d sub O times n minus k. N is 1 and k is 1, so times 1 minus 1. 1 minus 1 is 0, so this whole thing just disappears. Now, the first and only hit, right, because here we're assuming n equal 1, either does or does not trigger open wounds. Thus, the probability of beta sub 1 occurring is just p. So let's substitute that. This makes sense. The only way for open wounds to do any damage in time tau in this instance is if t sub n equals t sub 1 equals t bar is less than tau. Let's think about this. There's only been one hit, so we can't accrue damage from between hits. That means that the time at which that hit is delivered, if any damage is to accrue, needs to be such that when it's delivered, there's still a little bit of time left over. Meaning, really, our only option in this case is that damage can be accrued after all hits. In other words, beta sub 1. And we're scaling beta sub 1 by the probability this happens. So this makes perfect sense. Now, let's make sure this comports with our previous results. If p equals 1, then the result comports with our previous conclusion. Observe. D sub O sub 1 equals beta sub 1 times p. For p equal 1, so we're certain for this to happen, we just get beta sub 1. And substituting what beta sub 1 is shorthand for, remember, this is the cumulative damage accrued after all hits given only one hit. So R sub O times tau minus the time at which the first hit is given. That is tau minus T sub 1. Using our definitions, that's just minus 1 times T bar, which simplifies to T bar. Thus, D sub O sub 1 is equal to R sub O times tau minus T bar, which is exactly consistent with what we said previously. Assuming that we are certain to trigger on the first hit, and there's only one hit, we will accrue damage equal to R sub O times tau minus T bar. That is, open wounds will trigger on the first hit, and it will accrue damage at rate R sub O for a period of time equal to tau minus T sub 1, which in this case, under these assumptions, is just T bar. Okay. Suppose that we hit only n equal 2 times within time tau. Then the expected cumulative damage inflicted by open wounds against target X in time tau, using our formula, is given by D sub O sub 2 equals, the summation as k varies from 1 to 2, of alpha sub 2 of k, times p sub alpha sub 2 of k plus beta sub 2 times p sub beta sub 2. Let's evaluate the summation. Expanding, we have alpha sub 2 of 1 times p sub alpha sub 2 of 1 plus alpha sub 2 of 2 times p sub alpha sub 2 of 2. Applying our definition, we see that these are just equal to d sub O times 2 minus 1 and d sub O times 2 minus 2, right? The two possible cases for damage accrued between hits, depending on which kth hit activates open wounds. Simplifying, we see that in the second case, the right-hand case, that this is just d sub O times 0. All of that times 0 is just 0, right? Okay. The odds that open wounds first triggers on hit 1 is p. Remember that p sub alpha 2 of 1 is that probability. So p sub alpha 2 of 1 equals p, right? That is the case for damage accrued between hits in which open wounds is triggered on the first hit. So we are weighting the amount d sub O by the probability that it is accrued. This makes perfect sense. If there are only 2 hits to be accrued, there will be only one stack of damage between hits, d sub O. We will weight that based on the probability that it occurs, which is just p. If it triggers on the second hit, there's no damage between hits to be accrued because that is the last hit in the sequence. So this all makes complete sense. Substituting p for p sub alpha sub 2 of 1, we have d sub O of p plus beta sub 2 times p sub beta sub 2. How might we determine what p sub beta sub 2 is? Here's a visual aid. On the left-hand side, there's an orientation of time increasing from time t equals 0. And observe that all 2 hits are assumed to occur within time interval tau, which is marked at the bottom left. On hit 1, there are 2 possibilities with open wounds. It does or does not trigger, so yes or no. On hit 2, we have 4 possibilities, contingent on the previous possibility. What's the probability that it triggers on the first hit? Well, it's just p. What's the probability that it doesn't trigger on the first hit? It's just 1 minus p. What about the probability that it triggered on the first, and given that it triggered on the first, then it triggers on the second? That's the product of the probability that it succeeded on either hit. That's just p times p, or p squared. Okay. What about the probability that it fails to trigger on the second hit, but succeeded on the first hit? Well, that's just the product of the probabilities, p times 1 minus p. What about the probability that it succeeds on the second hit, but failed on the first? That's the product of the probabilities of success and failure, so p times 1 minus p. And what about the probability that it failed on both hits? That's just the product of two consecutive failures. So 1 minus p times 1 minus p, or 1 minus p to the second. Now, we're going to ask for each of these cases, does open wounds accrue damage after all hits in time tau minus t sub 2? Since there are only 2 hits, that's why it's t sub 2. We're doing that because we want to know the instances in which we're actually going to get beta sub 2, right? Damage ticking over time. Which, remember, is independent of k. That is when it first triggers. We just want to know whether it did. Because per our assumptions, we're still assuming that everything occurred within time tau. So we don't have to look at instances in which open wounds has expired. We're only asking, essentially, for the beta component, has it gone off yet? So, does open wounds accrue damage after all hits in the instance that the first one triggers? Yes, it does. What about in the instance that the second one triggers and the first one succeeded? Yes. And what about the instance in which the second one fails but the first one triggered? Still yes, because remember, we're still within the time interval tau, which is less than or equal to the duration of open wounds. Okay. What about the instance in which it did not trigger on the first hit? It's unclear. We have to wait until the second hit to determine that, right? If the second hit triggers on the assumption that the first failed, we will get damage accrued after all hits. So this is a yes. And thus, the only instance in which we will not have damage accrued after all hits in time tau minus t sub 2 is when we have 2 successive failures. That means 1 minus p to the second power is the probability this will not occur. That is, the probability that we will not accrue damage after all hits within time tau minus t sub 2. So the only instance in which open wounds does not accrue damage after all hits in time tau minus t sub 2 is when all 2 hits fail to trigger open wounds. And since 1 minus p to the second is the probability of failure, 1 minus that probability is the probability of success. That is to say, thus the odds that open wounds accrues damage after all hits in time tau minus t sub 2 is 1 minus p to the second power. Now, going back to the initial statement, the only instance in which open wounds does not accrue damage after all hits in time tau minus t sub 2 is when all 2 hits fail to trigger open wounds. Do you observe that if we continue down this probability tree, this will always be the same, right? We can generalize this for any nth hit. We could argue by mathematical induction if need be, but I think it's pretty self-evident, right? We can generalize this to any n hit then. That is, the only instance in which open wounds does not accrue damage after all hits in time tau minus t sub n is when all n hits fail to trigger open wounds. Thus, the same logic applies. The odds that open wounds accrues damage after all hits in time tau minus t sub n is 1 minus p to the n power. Using this, let's go back to the initial question. How might we determine p sub beta sub 2? Thus, the odds of beta sub n occurring are 1 minus p to the n for all n and z positive, because the only case in which open wounds will not deal damage at rate r sub o over time tau minus n t bar is when all n hits fail to trigger open wounds. Indeed, for in the previous case when n equals 1, we see that d sub o sub 1, which we determined to be equal to beta sub 1 times p, is actually just this expression in disguise. Observe. P is equal to 1 minus 1 plus p. Notice the 1 minus 1s will cancel. It's the same thing, right? But that is just equal to 1 minus p, which is 1 minus p to the first. So for n equal 1, we already see that our results previously comport with this. Thus, we have that when n equals 2, we observe that p sub beta sub 2 equals 1 minus p to the second power. Let's substitute that in. And that's our d sub o sub 2. All right, let's make an addendum to our previous equation pertaining to the cumulative damage. Given that beta sub n is equal to 1 minus p to the n for all n and z positive, it follows that, given a sequence of n and z positive consecutive hits, h1, h2, hk, hn, made against a single target x in time tau, the expected cumulative damage inflicted by open wounds against target x in time tau, denoted d sub o sub n, is given by. So there's our previous equation. Let's substitute p sub beta sub n. All right, that's looking better. Let's see if we can simplify p sub alpha sub n of k in a similar fashion. To do this, let's look at n equal 3. We might glean better insight. Suppose that we hit only n equal 3 times within time tau. Then using this formula, the expected cumulative damage inflicted by open wounds against target x in time tau is given by d sub o sub 3 equal to the summation as k goes from 1 to 3 of alpha sub 3 of k times p sub alpha sub 3 of k plus beta sub 3 times 1 minus p to the third power. Let's expand the summation. Let's simplify. By definition, we have that d sub o times 3 minus 1, d sub o times 3 minus 2, d sub o times 3 minus 3, right? We're just substituting 3 minus 1, 3 minus 2, 3 minus 3. Observe that d sub o times 0, all of that is just 0, right? So that goes away. Now remember what p sub alpha sub 3 of 1 is. It's when open wounds first triggers on the first hit, which is not necessarily the same as the probability that open wounds triggers on any particular hit. In this case, it is, right? The odds that open wounds triggers on the first hit is just p. So p sub alpha sub 3 of 1 is just p. So let's substitute. The probability that open wounds first triggers on the second hit, however, is different. It is the probability it triggers on the second hit given that it failed to trigger on the first hit, which is the product of the probabilities it failed and succeeded. In other words, p sub alpha sub 3 of 2 is equal to p times 1 minus p. So let's substitute that. Here's something interesting. This pattern will persist for all subsequent hits. The odds that open wounds triggers on the third hit, given that it failed to trigger on the first 2 hits, is the product of the probability of 2 failures and the probability of 1 success. So that means that p sub alpha sub 3 of 3 will be 1 minus p times 1 minus p times p, which is just p times 1 minus p to the second power. So more generally, the odds that open wounds triggers on the kth hit, given that it failed to trigger on the first k minus 1 hits, is the product of the probability of k minus 1 failures and the probability of 1 success. That is, p sub alpha sub n of k is equal to p times 1 minus p to the k minus 1 power for all k and n z positive, such that k is less than or equal to n. Thus, p sub alpha sub n of 1 is equal to p times 1 minus p to the 0 power. Notice that we have that above. P times 1 minus p to the 0 power is just 1, which is just p, right? So the 2 d sub o times p already satisfies that. Similarly, p sub alpha sub n of 2 is p times 1 minus p to the first power, which we have above. P sub alpha sub n of 3 is just p times 1 minus p to the second, and so forth. P sub alpha sub n of k is equal to p times 1 minus p to the k minus 1 power. Thus, p sub alpha sub n of k is just p times 1 minus p to the k minus 1 for all k, n, and z positive, such that k is less than or equal to n. Remember, these are instances in which open wounds first triggers on that hit. So it makes perfect sense that we need k minus 1 successive failures and then 1 success. Remember that because all this is happening within time interval tau and we're not exceeding tau, we don't need to worry about instances in which open wounds expires. It's just a question of whether it's gone off yet, etc., etc. Just to confirm, our second term then, p times 1 minus p, that is just p times 1 minus p to the first, which is consistent with these results. In addition, p is just p times 1, which is times 1 minus p to the 0. So indeed, this comports with our results. Notice that in the previous case, when n equal 2, we have this equation, right? That p term is actually p times 1, which is p times 1 minus p to the 0. So when n equals 2, this also comports with our results. Just compressing that back to what we had initially, which we'll be using later. So given that p sub alpha sub n of k is equal to p times 1 minus p to the k minus 1 for all k, n, and z positive such that k is less than or equal to n, it follows that, given a sequence of n and z positive consecutive hits, h1, h2, hk, hn, etc., made against a single target x in time tau, the expected cumulative damage inflicted by open wounds against target x in time tau, denoted d sub o sub n, is given by, here's our equation. Let's plug in what we have for p sub alpha sub n of k. Okay, notice that p is constant. So let's factor that out of the summation. Now, recall that alpha sub n of k is equal, by definition, to d sub o times n minus k for all k, n, and z positive, such that k is less than or equal to n. So let's plug that in. D sub o is constant, so let's factor that out of the summation. And now we have this nice equation. Let's test this to make sure it's correct. Let us verify that this yields the expected results. For n equal 1, we have d sub o sub 1 equals d sub o times p times the summation as k varies from 1 to 1 of 1 minus k times 1 minus p to the k minus 1 power plus beta sub 1 times 1 minus p to the 1. Let's evaluate the summation. 1 minus 1 is just 0. So this whole thing is just 0, right? That's all just 0. Okay. 1 minus p to the first is just 1 minus p. And the opposite of 1 minus p, that's just going to be negative 1 plus p. This whole thing is just p. D sub o sub 1 equals beta sub 1 times p. We showed previously that d sub o sub 1 is beta sub 1 times p. This comports with our findings thus far. Okay, what about for n equal 2? Well, for n equal 2, we have this formula. Again, that we have the summation as k varies from 1 to 2 this time. So let's evaluate the summation. Observe that 2 minus 1 and 1 minus 1, that's just going to be 1 times 1 minus p to the 0. All of that's just 1, right? 2 minus 2, the important thing is 2 minus 2 is 0, so that whole thing, that's just 0, right? And indeed, that's just 1. That's just d sub o times p. What did we have for d sub o sub 2? We showed previously that d sub o sub 2 is d sub o p plus the beta sub 2 times 1 minus p to the second power. So this comports with our results as well. And lastly, for n equal 3, our summation varies from 1 to 3. So let's expand the summation. Let's evaluate these coefficients here. 3 minus 1, minus 2, minus 3. Drawing your attention to the 0 times that is just 0, right? Okay, 1 minus 1, 2 minus 1, that's just 0, and then to the first power. This, in turn, will simplify as follows. 2 times 1, and then 1 minus p to the first is just 1 minus p, right? 2 times 1 is just 2. Let's distribute d sub o times p over these two things. Indeed, what we had previously was exactly what we have now. So this does comport with our findings thus far. Okay. Now this is why we assumed earlier that p is in the interval 0, 1, but not equal to 0 or 1. Because for all n and z positive, and for all p in the interval 0, 1, the summation as k varies from 1 to n of n minus k times 1 minus p to the k minus 1 power is equal to 1 minus p to the n plus np minus 1 over p squared. This is pretty easy to prove by mathematical induction. However, given the length of this video, I thought I'd exclude it. However, if you would like a proof, let me know in the comments. I'll be happy to oblige. Given this, we can now substitute. So let's do that. Given a sequence of n and z positive consecutive hits, h1, h2, hk, hn, made against a single target x in time tau, where p is in 0, 1, and is the probability to trigger open wounds on hit k for all k and z positive such that k is less than or equal to n, it follows that the expected cumulative damage inflicted by open wounds against target X in time tau, denoted d sub O sub n, is given by this formula. Now let's substitute the summation for what it's equivalent to under the right constraints. We see that the p's cancel. Recall that beta sub n is equal to r sub O times tau minus nt bar for all n and z positive. Let's substitute that into this equation. Recall that d sub O is just r sub O times t bar. Right, so that notational change was just for brevity. Factoring out the r sub O, we now have a nice equation where r sub O is the damage per unit time in seconds inflicted by open wounds. This is what you would look up on, an applicable website. It scales with level, etc., etc. T bar in the interval 0 tau inclusive is the mean time between hits in seconds. We can reduce the number of variables in this equation because the number of hits n and z positive that a character will deliver in time tau will depend on the relationship between tau and t bar. So let's do that. Recall that if t bar is the mean time between hits, then t sub n equals n t bar for all n and z positive. Observe that we must have, as previously discussed, that 0 is less than or equal to tau minus t sub n less than t bar for all n and z positive, as tau minus t sub n greater than or equal to t bar would contradict our assumption that only n hits were made against target X within time tau. Here's a visual reminder, right? The remaining time, that is the time needed for n plus 1 equal 5 hits in this counterfactual hypothetical in which 4 hits were delivered, is insufficient. Thus, it follows that under these constraints, tau minus t sub n must be less than, per assumption, t bar. This means tau minus n t bar must be less than t bar. This means that tau must be less than t bar plus n t bar. Factoring out t bar, tau must be less than t bar times n plus 1. Thus, tau over t bar must be less than n plus 1. So, tau over t bar must be less than n plus 1 for all n and z positive. Okay? Also, given that 0 must be less than or equal to tau minus tn for all n and z positive, it also follows that for all n and z positive, that 0 is less than or equal to tau minus t sub n, as we just said, and that t sub n thus is less than or equal to tau. Applying our definition, n t bar must be less than or equal to tau, and so n must be less than or equal to tau divided by t bar. So tau over t sub n must be greater than or equal to n for all n and z positive. Putting these two things together, given that tau over t bar is greater than or equal to n, and tau over t bar is less than or equal to is strictly less than n plus 1 for all n and z positive, it follows that for all n and z positive, tau over t bar is greater than or equal to n and strictly less than n plus 1. Care must be taken when interpreting this equation correctly. We are not saying that you can put any integer into this equation and it will be correct, but rather for those n occurring within time tau, right? Then for any of those n, in every case that's applicable, this equation will be satisfied. I want to make sure that's clear. Meaning this is true for all n given the implication that to assume n hits have occurred means they are occurring within time tau. Okay, this implies that for all n and z positive, there exists an epsilon in the interval 0 inclusive 1 exclusive, such that tau over t bar equals n plus epsilon. In other words, epsilon can be 0, but it cannot be equal to 1, as that would mean that tau over t bar is equal to n plus 1, which it's strictly less than. Thus, tau over t bar is equal to n plus epsilon, for epsilon in the aforementioned interval. Okay, given that tau over t bar equals n plus epsilon, where n is a positive integer, and epsilon is in the interval 0 inclusive 1 exclusive, it follows that for all n and z positive, such that tau over t bar equals n plus epsilon, where epsilon is as defined before, that the floor function of n plus epsilon equals the floor of tau over t bar. Now the floor function is just a function that takes in a real number and spits out an integer less than or equal to that real number. It is the greatest integer less than or equal to that real number. So for example, let's say I have the floor of 3.2, then 3 is the result. Okay, that means that because epsilon is strictly less than 1 and greater than or equal to 0, that n is equal to the floor of tau over t bar for all n in z positive, satisfying what we said above. Thus, the floor of tau over t bar equals n for all n in z positive such that tau over t bar equals n plus epsilon, where epsilon is as defined before. Okay, now let's use this in our previous equation. Given that tau over t bar equals n for all n in z positive such that tau over t bar equals n plus epsilon, where epsilon is as defined before, it follows that this expression can be simplified. So let's do that. All of these n's are just the floor of tau over t bar. Okay. Thus, given an applicable, and I'm emphasizing applicable because I think I've motivated up to this point what kind of hit sequences we're talking about. So given an applicable sequence of consecutive hits made against a single target X in time tau, it follows that the expected cumulative damage inflicted by open wounds against target X in time tau, denoted d sub o of p t bar, is given by this equation, where p in the interval 0, 1 exclusive is the probability to trigger open wounds. R sub o is the damage per unit time in seconds inflicted by open wounds that we'd look up on an applicable website based on level. T bar in the interval 0 tau inclusive is the mean time between hits. And in case it wasn't emphatically clear, we are not allowing T bar to be 0. It's worth noting that we've implicitly accounted for probability here. The reason is that if there is some probability that any particular hit lands for all hits occurring within some time tau, then we can scale T bar accordingly to some analogous T bar given the chance that any particular hit lands. Okay. There are 4 major cases we need to check to make sure this equation makes sense. First, when T bar equals tau. As in such instances, notice that if T bar equals tau, there's been one and only one hit, so there's no damage accrued from between hits, and since the time at which the first hit and only hit is given is equal to the time tau, there will be no time remaining for damage to accrue after all hits. In other words, there will be no damage from either component. The total damage should be 0. This equation, if correct, should satisfy this condition. Second, when T sub n equals tau. In such cases, all of the damage needs to be coming from in between hits. There will be no time after T sub n is delivered for any damage to accrue after all hits. Third, when T bar equals tau minus epsilon for epsilon in the interval 0 T bar. Here's a picture illustrating such a case. So to say T bar equals tau minus epsilon is to say there's been one and only one hit, and that the time at which the hit is delivered is such that there's not enough time for another hit to occur, so there'll be no damage between hits. However, there should be some amount of damage to accrue in this interval of time after all hits have been delivered. And the amount of damage should be equal to R sub o times tau minus T bar. But the key takeaway here is in this case, there's no damage from between hits, but all damage is accrued from after all hits. Lastly, when P equals 1. In such an instance, open wounds is certain to trigger on a particular hit. It will trigger on the first hit, giving us R sub o accruing over the maximum time interval possible, tau minus T bar, as indicated in this picture. Okay, let's start with the first instance. Let us verify that if T bar equals tau, then d sub o of P tau equals 0. Okay, plugging in T bar equal tau, we have the following. Now, tau over tau is just 1 for all tau, so it simplifies as follows. Cleaning that up, we have the resulting expression. 1 minus p to the first power, that's just 1 minus p. And if we apply a negative to that, that's just 1 minus 1 plus p. So this whole expression is just P. Tau minus tau is just 0. So this whole thing is just 0. So that's just 0. Okay, 1 minus p to the first power is just 1 minus p. And summing all those terms up together is just 0. This whole thing is therefore just 0. And r sub o times 0 is just 0. So sure enough, we have that when t bar equals tau, it follows that d sub o p tau equals 0. Okay, so far so good. Next, let's see what happens when t sub n equals tau. Now remember, we want all damage only to be coming from the damage accrued between hits. So the second component needs to disappear entirely. Now, if t sub n equals tau, then per our definitions, n t bar will equal tau, implying that t bar equals tau over n, and n equals tau over t bar. So using this first one, substituting t bar equal to tau over n, we have the following. The reason I didn't substitute tau over n in the t bar on the left-hand side, you'll see why in a second. Okay, and then we have n equal tau over t bar. Let's substitute that into this equation. The floor of n, since n is an integer, is just n, right? Okay. Notice that there's a cancellation of n's here. So we really just have tau minus tau. That's just 0. So this whole thing is just 0. So that's pretty good. We can factor out the t bar. Remember that we defined a d sub o to be r sub o times t bar. So sure enough, the second component goes away entirely, and what remains is only the component of damage accrued cumulatively between hits in time tau. Just to make sure this is consistent with our previous findings, suppose that p equals 1. Then plugging that into this equation, we have the following, right? We simplify. 1 minus 1 is just 0, so 0 to the n for any finite n is just 0. D sub naught times n minus 1. This makes sense and is consistent with our findings earlier. If we are certain to trigger open wounds, then it will trigger on the first hit, dealing d sub o times n minus 1, which is the same as d sub o times n minus k for k equals 1, cumulative damage between hits. There is no secondary component, as t sub n equals tau, as previously mentioned, implying that there is no remaining time for open wounds to deal any damage in time tau after all hits have been made. Okay. Now, let's see what happens when t bar equals tau minus epsilon, where epsilon, as mentioned before, is in the interval 0 t bar. Observe that t bar plus epsilon is tau by assumption, so t bar plus epsilon over t bar is tau over t bar. Simplifying, t bar over t bar is 1, so this is just 1 plus epsilon over t bar equals tau over t bar. Thus, tau over t bar equals 1 plus epsilon over t bar. Let's use this. So given t bar equal tau minus epsilon, we'll substitute that. Recall that tau over t bar equals 1 plus epsilon over t bar as previously established. So substituting that for tau over t bar, we have 1 plus epsilon over t bar for all these instances. Okay, now the floor of this, how do we evaluate that? Well, given that epsilon is in the interval 0 t bar exclusive, it follows that epsilon over t bar is less than 1, because epsilon is less than t bar. So using this, we can evaluate the floor of 1 plus epsilon over t bar as just 1. So let's do that. And sure enough, it simplifies as follows. So far, so good. Now, 1 minus p to the 1 power, that's just 1 minus p. And sure enough, all of this cancels to 0. And of course, that's to 0. And so this whole thing is 0, right? And so the first component disappears entirely. Now, what about this? 1 minus p to the first, again, is, if we have the minus sign there, minus 1 plus p, right? And so this whole thing is just p. We don't need those outer parentheses. So r sub o times tau minus t bar times p. Let's see if this is also consistent with previous findings. Now, if p is 1, then d sub o 1 tau minus epsilon is just r naught times tau minus t sub n when n is equal to 1, right? Giving us t bar in place of t sub n, which is also consistent with what we found earlier. If we are certain to trigger open wounds and we hit only once, there's no damage accrued between hits, but open wounds will accrue damage for the remaining time tau minus t sub n where n equal 1 after all hits have been made. Good thus far. Now let's see what happens when p equals 1. So when p equals 1, plugging this into our formula for p, we have the following. Okay, simplify. Now, 1 minus 1 is just 0, so this whole thing is just 0 right there. Same here, that's 0, 0 to a finite power, 0, 1 minus 0 is 1. We don't need the parentheses. Okay, let's distribute t bar to these two terms. Observe that t bar times the floor of tau over t bar cancels with negative floor tau over t bar times t bar. So these two terms cancel, and sure enough, r sub o times tau minus t bar is what we get when p is 1, exactly as we would expect. Now, given that this equation behaves as we expect it to for p equal 1, we can relax the restriction that p is in the interval 0, 1 exclusive and allow for p to be greater than 0 and less than or equal to 1. So let's do that and make an addendum to our existing equation. Given an applicable sequence of consecutive hits made against a single target X in time tau, it follows that the expected cumulative damage inflicted by open wounds against target X in time tau, denoted d sub o of p t bar, is given by this equation, where p is greater than 0 and less than or equal to 1 and is the probability to trigger open wounds. R sub o is the damage per unit time in seconds inflicted by open wounds, what you would look up on applicable websites that scales with character level. And t bar in the greater than 0 and less than or equal to tau is the mean time between hits in seconds. Now remember, tau itself is greater than 0 and less than or equal to 8 seconds. Now, there are two components here. The first component is the expected cumulative damage accrued from between hits in time tau, right? And that's indicated here in red. The second component is the expected cumulative damage accrued after all hits in time tau. That's indicated here in red. And then we have this scaling factor. So we've left it in this form to allow us to see each of these parts. Now let us analyze the first part, the expected cumulative damage accrued between hits in time tau, given by this, when I distribute the r sub o. We'll graph this to see how it varies for various values of p and t. First, for p equal 1. So we're going to assume p equals 1. So how do we interpret this graph? The vertical axis denotes the expected cumulative damage inflicted by open wounds against target X in time tau. Hence, a value along the vertical axis of d sub o of p t bar equals 0 would mean that 0 expected cumulative damage was inflicted by open wounds against target X over time tau. The horizontal axis denotes the mean time between hits in seconds. Hence, a value along the horizontal axis of t bar equal tau would mean that the mean time between hits in seconds is tau, implying that only a single hit occurred with no time after all hits have been delivered remaining in time tau. Now, if the target was already suffering from open wounds at time t equals 0, again, we're not assuming that's the case, we're just saying counterfactual, like in a counterfactual hypothetical, okay? If that were the case, then open wounds would accrue damage at rate r sub o for a period of time tau seconds, resulting in a cumulative total of r sub o times tau damage from open wounds in time tau. This is the purple horizontal line. Recall that this is the graph of the component pertaining to the expected cumulative damage accrued between hits in time tau, when p equals 1. We showed previously that d sub o of 1 t bar equals r naught times tau minus t, which makes sense. The first hit is certain to trigger open wounds under these assumptions, and so open wounds will accrue damage at rate r sub o for a period of tau minus t bar seconds, resulting in r sub o times tau minus t bar cumulative damage from open wounds in time tau. Thus we know that d sub o of 1 t bar must be equal to r sub o times tau minus t bar. So let us graph d sub o of 1 t bar equal to r sub o times tau minus t bar to see how much of d sub o of 1 t bar for various values of t bar comes from the expected cumulative damage accrued between hits in time tau. In other words, we want to see how much of that is from the cumulative damage between hits. we know that the cumulative damage between hits and after all hits must sum to this black line when p equals 1, which again, this component of the damage accrued from between hits is when p equals 1. So it's going to be the component from between hits. The remainder must be the component from after all hits. And that's indicated here by that diagonal dotted black line. Now, if t bar equals tau over 2, then the expected cumulative damage accrued between hits in time tau is r sub o tau over 2, as indicated on this graph. This makes sense, as t bar equals tau over 2 implies that tau over t bar floor is equal to n, which is 2 in such instances. If 2 hits are made with no remaining time after all hits have been made, then given that p equals 1, it follows that the first hit will occur at tau over 2 seconds, and it will trigger open wounds, which means that r sub o will accrue for a period of tau over 2 seconds, the expected time taken to score the second hit. Thus, r sub o tau over 2 damage should be dealt in total. So this makes sense. It's also worth noting that this is a case in which t sub n equals tau, so all of the expected cumulative damage should come from that accrued between hits. We should verify that this is the case for the second component of our equation, that is the damage accrued after all hits, when t bar equals tau over 2. Okay, for a given value of t bar, the difference between the red curve and the dotted black line is going to be the difference from the expected cumulative damage accrued after all hits in time tau. Remember, the red that we see here must add to something such that they both equal r sub o times tau minus t bar. Why are there jumps? There are jumps in this equation because these are instances in which tau is or is not wholly divisible by t bar for that particular value of t bar. So that makes sense. Observe also what happens when t bar approaches 0, that is when t bar gets smaller and smaller. The expected cumulative damage accrued after all hits gets smaller. So unsurprisingly, as t bar goes to 0, the expected cumulative damage accrued between hits in time tau converges to r sub o tau, and the expected cumulative damage accrued after all hits in time tau converges to 0. Maybe this isn't obvious at first, but let's think about it. This does make sense, because we require that 0 is less than or equal to tau minus t sub n, which is less than t bar. Thus, as t bar goes to 0, tau minus t sub n must also go to 0, because tau minus t sub n is less than t bar. This of course implies that since the distance between these things is going to 0, t sub n essentially converges to tau as t bar goes to 0. Thus, less and less time will remain for open wounds to accrue damage after all hits, implying that the expected cumulative damage after all hits in time tau converges to 0. Right? That's what's going on here. Furthermore, t bar converging to 0 would just mean that open wounds will be triggered that much sooner. Because recall that we assumed in this instance that p equals 1. It would eventually be analogous to having simply inflicted r sub o damage for all tau seconds, right? Resulting in a cumulative sum of r sub o tau damage. Okay. Why is the expected cumulative damage from open wounds accrued between hits in time tau equal to 0 for all t bar greater than tau over 2 seconds? Well, if t bar is greater than tau over 2, then 2t bar is greater than tau. So what? Well, that implies that tau over t bar is less than 2. And so taking the floor function, tau over t bar equals n equals 1. So there was no damage accrued via open wounds between hits in such instances because there's only one hit in the sequence made. So there's no between hits that's applicable. That would be why. That means in such instances, all the expected cumulative damage accrued in time tau, right, which we know must be equal to r sub o times tau minus t bar, because p equals 1, must come from the second component of this equation in such instances. And of course, we'll verify, looking at the second component, that this is the case. Okay, so in summary, for all t bar in the interval 0, tau, excluding 0 including tau, the expected cumulative damage accrued between hits and after all hits in time tau must sum to r sub o times tau minus t bar when p is 1. As t bar goes to 0, the expected cumulative damage accrued between hits in time tau converges to r sub o tau, and the expected cumulative damage accrued after all hits in time tau converges to 0. Now, as t-bar approaches tau, the expected cumulative damage accrued after all hits in time tau converges to 100% of that damage, right? And the expected cumulative damage accrued between hits in time tau converges to 0% of that damage, such that the expected cumulative damage from open wounds accrued between hits is 0 for all t-bar greater than tau over 2, with the exception being right at, t-bar equal tau, right? That's when it's all 0, but a limit isn't really concerned with what's happening at that point, but around that point, so that's fine. The TLDR is that we should have these things mirrored in the plot for the damage accrued after all hits. So how does probability change things? So here's a plot. The blue curves are the upper and lower bound, when p equals 1 and when p equals 0.01, respectively. The red plot is some value between the upper and lower bound. Let's add our dotted black line. Okay, so let's see how allowing p to vary changes things. Okay, so just as before, the black horizontal line up top corresponds to r sub o, tau. The green diagonal line corresponds to the black dotted line on our graph, so that's going to be r sub o times tau minus t bar. The blue curves are the upper and lower bounds respectively for various values of p, where the upper bound is for p equal 1 and the lower bound is for p equals 0.01. The red curve is a plot for some value of p that varies between 0.01 and 1 inclusive. Let's see what happens when we let probability range. So that's for p equal 1, and now the probability drops. And again, this is for the cumulative damage accrued from between hits. Okay. Now, let us analyze the expected cumulative damage accrued after all hits in time tau, given by this if we distribute r sub o. We shall graph this to see how it varies for various values of p and t bar, first for p equal 1, just as before with the first component. Let's add our dotted black line. We observe that the expected cumulative damage accrued after all hits in time tau is equal to r sub o times tau minus t bar for all t bar greater than tau over 2, as expected, right? No damage is missing, all of that damage is being done by the second component, right? In other words, all of the damage comes from that accrued after all hits when t bar is greater than tau over 2. We also observe that the expected cumulative damage accrued after all hits in time tau converges to 0 as t bar goes to 0, as expected. Also, the expected cumulative damage accrued after all hits in time tau is 0 when t bar equals tau over 2, as expected. Given that the expected cumulative damage accrued between hits in time tau is r sub o tau over 2 equal to r sub o times tau minus t bar for t bar equal tau over 2, it follows that the sum of both components is r sub o tau over 2 equal r sub o times tau minus t bar as expected when p equal 1 in this instance. So that's good. How does expected cumulative damage accrued after all hits in time tau vary with respect to probability? Okay, just as before, the black horizontal line corresponds to the value r sub o tau, and the green line corresponds to the black dotted line. So that's going to be r sub o times tau minus t bar. That would be the green line. Let's see how the cumulative damage accrued from after all hits varies over various values of p, from p equal 1 all the way down to p equals 0.01. So that's 0.01, and that's p equal 1. So it appears that everything's just scaled with respect to probability, right? Now we shall put these together and graph the expected cumulative damage inflicted by open wounds against target X in time tau given by this formula. So let's do that. The blue curves are the upper and lower bound, respectively, for various values of p. For p equal 1, as before, it converges to a linear equation of r sub o times tau minus t bar. And the floor we have set for p equals 0.01, because in Diablo 2 Resurrected, there is no smaller denomination for a percentage for probability. The red curve is then some probability between those two. Okay, so let's see how allowing p to vary changes things. Okay, as before, the black horizontal line is r sub o times tau. The blue curves are the upper and lower bound, respectively, for varying values of p. The red curve will vary for p greater than or equal to 0.01, less than or equal to 1. So let's see how this curve varies as we let p vary over this interval, that is from 0.01 to 1 inclusive. So there's the lower bound, there's the upper bound. We observe that d sub o of p t bar is greater than or equal to 0 and less than or equal to r sub o times tau minus t bar for all p in 0 exclusive 1 inclusive, and for all t bar in 0 exclusive tau inclusive. In other words, these are lower and upper bounds for this function. Okay. How can we calculate the analogous expected damage per second inflicted by open wounds against target X in time tau, since we now have a formula for the cumulative damage? Well, if d sub o of pt bar is the expected cumulative damage inflicted by open wounds against target X in time tau, then dividing d sub o of pt bar by tau will result in the analogous expected damage per second inflicted by open wounds against target X in time tau. That is this formula. Okay. Given the upper and lower bounds we've established before, right? That is that d sub o of pt bar is greater than or equal to 0 and less than or equal to r sub o times tau minus t bar for all p in 0 exclusive 1 inclusive, and for all t bar in 0 exclusive t bar inclusive. It follows that for all p in 0 1 and for all t bar in 0 tau, that dividing all sides of this inequality by tau, we have these expressions. That simplifies as follows, and if we distribute the tau inside of those parentheses, tau over tau is 1. So we end up with these upper and lower bounds for the damage per unit time inflicted by open wounds over time tau. Okay, putting all of this together. Given an applicable sequence of consecutive hits made against a single target X in time tau, it follows that the analogous expected damage per second inflicted by open wounds against target X in time tau, denoted d sub o of p t bar bar, is given by this formula, where p in the interval 0 exclusive 1 inclusive is the probability to trigger open wounds on any particular hit. That's essentially the percent open wounds on your item. R sub o is the damage per unit time in seconds inflicted by open wounds, which you would look up on applicable websites. T bar in the interval 0 exclusive, tau inclusive is the mean time between hits in seconds. And d sub o of p t bar bar is greater than or equal to 0 and less than or equal to r sub o times 1 minus t bar over tau. That is, those are the upper and lower bounds of this formula. Remember that I'm emphasizing in bold here applicable sequences of consecutive hits. So we're not ideally alternating weapons, although again, in some instances in which these parameters are unchanged, you can feel free to do so. Additionally, if you wish to account for chance to hit, you can adjust T-bar accordingly. Another thing to note is that the only difference between this and the previous equation is the 1 over tau factor, right? So in terms of the shape of the graph and the implications, nothing will change except the vertical axis. But I'll show you the graph anyway. So sure enough, there's our graph. The only difference here is now the vertical axis is the measure of the mean analogous damage inflicted per unit time over the interval of time tau, right? That means that instead of R0 times tau, we're looking at just the rate R0, which is what you would look up at applicable websites, right? So now we're seeing how much of that we're actually doing with respect to various values of T-bar. As before, the blue curves are lower and upper bounds respectively. where the upper bound is for p equal 1 and the lower bound is for p equals 0.01. The red curve is then for some value of p between the upper and lower bounds. Okay. Just as before, let's see how allowing p to vary changes things. The red curve will vary for p greater than or equal to 0.01, less than or equal to 1. So let's see how this curve varies as we let p vary over this interval, that is from 0.01 to 1 inclusive. So there's the lower bound, there's the upper bound. All right, now let's do some examples. So we have this equation, now let's use it in an example to see if it actually does what we intended it to do. Let's test this equation with the following example. Suppose that R sub O does 1.2 damage per second, that a character hits a target 3 times in 8 seconds such that the time between each hit is 2.5 seconds, and that said character has a 2 in 3 chance to trigger open wounds per hit. Now, given that R sub O equals 1.2 and T bar equals 2.5, it follows that D sub O equals R sub O times T bar, which is 3. In other words, that's going to be the expected damage between hits. Also, T bar equal 2.5 and N equal 3 implies that T sub 3 is expected to be 3 times 2.5 or 7.5, implying that tau minus T sub 3 is going to be 8 minus 7.5 is 0.5. So here's a table to go along with the probability tree. So let's look at the instance in which open wounds first triggers on hit 1. Well, if it does, then there will be 2 subsequent hits after the first hit over which it will accrue, right? So there will be 2 stacks of the damage between hits if it triggers on the first hit, given that there are 3 in total. Since D sub O is 3 and there are 2 stacks, we should expect to have 6 cumulative damage in such instances from the damage between hits. After the third hit, R sub O will accrue for a period of 0.5 seconds, so we should expect that 0.6 will be the damage accrued in such instances from the damage accrued after all hits. Given these 2 amounts, in such instances we would expect a cumulative damage of 6.6 damage. This makes sense. Note that R sub O times tau minus T bar equals 1.2 times 8 minus 2.5, which is 6.6. So this makes sense. In the second case, it's the same thing, right? We have 2 stacks, 3 times 2 is 6, it's going to accrue at a rate of 1.2 for 0.5 seconds. The cumulative sum should be 6.6, so nothing different there. Okay, what about when it fails on the first hit? Let's look at the 2 instances in which it will succeed on the second hit given that it failed on the first. In such instances, there's only 1 hit remaining over which it can accrue damage. So there's only 1 stack in such instances, right? So D sub O times that 1 stack will only expect to accrue 3 damage in such instances. It will still deal damage of 1.2 over a period of 0.5 seconds. So we would expect this amount of cumulative damage after all hits. Putting these together, we would expect 3.6 cumulative damage from open wounds in such instances. This makes sense because R sub O times tau minus 2 T bar, right, equals 1.2 times 8 minus 2 times 2.5, which is 3.6. So this makes sense. All right, let's say it fails to trigger on the second hit. Then there's only 1 option left, right? It will trigger on the third hit. But if it does so, there's no between hits that can apply, right? There are no stacks over which it can accrue. So the damage it does between hits times 0 is just 0. So we're not going to get any damage from between hits, but there will be some period of time, right, 0.5 seconds, over which it will still accrue at rate 1.2 per second. So we'll still get 0.6 cumulative damage, right? Summing these together, that's what we see. And again, this makes sense because R sub O times tau minus 3 T bar equals 1.2 times 8 minus 3 times 2.5, which is just 0.6. So that makes sense. In the last instance, we'll have 0 stacks, so there will be no damage between hits, and because there's only 0.5 seconds, but it didn't trigger, no damage will accrue over that interval because it did not trigger, right? It's 3 no's in a row, and so 0 plus 0, no damage accrues in that instance. So this is how we produce this table. The mean of all these cumulative sums is 5.24 repeated. That is the mean expected damage over this interval of time tau will be 5.24 repeated. So if we inflicted an expected cumulative damage of 5.24 repeated over a period of time of 8 seconds, then the analogous expected damage per second inflicted by open wounds against target X in time tau equal 8 seconds is given by 5.24 repeated divided by 8, which is equal to 0.65 repeated. Thus, if our equation is correct, then we must have the d sub O of 2/3 2.5 bar equals 0.65 repeated when tau is 8 and r sub O is 1.2. Let's see what happens. Plugging all these values into this equation and then evaluating the result, indeed, we see that we get 0.65 repeated. So this equation correctly predicts the result in this instance and all the instances covered in the domain of discourse. Note that if you had simply approximated, as many people do, the analogous expected damage per second inflicted by open wounds against target X in time tau as r sub O, right, equal to 1.2 damage per second. In other words, you just added the damage per second from open wounds to your damage per second, then you would have been off by a non-trivial factor. As we see that the actual analogous damage per second inflicted by open wounds against target X in time tau is better approximated in this instance, as only 54.629 repeated percent of r sub O. Implying that even had you multiplied r sub O by 2/3, right, your chance, you'd still been overestimating, as the better approximation is only 81.94% of 2/3 r sub O in this case. Okay, there's something else I want to cover then, since we're talking about, adding this to damage per second. You'll be pleased to know that you can add the analogous expected damage per second inflicted by open wounds against target X in time tau to existing damage per second, as long as there are no obvious conflicts, right? However, care must be taken. So what do we mean by care must be taken in such instances? I'll use an example to illustrate this. Suppose that r sub O is 16 damage per second, that a character who inflicts 1 to 3 damage inclusive per hit hits a target 2 times in 4 seconds, such that the time between each hit is 1.75 seconds, and that said character has a 1 in 2 chance to trigger open wounds on hit. Given that r sub O equals 16 and t bar is 1.75, it follows that d sub O equals r sub O t bar equals 28. Also, t bar equal 1.75 and n equal 2 imply that t sub 2 equals 2 times 1.75 equals 3.5, implying that tau minus t sub 2 equals 4 minus 3.5 is 0.5. So here's our resulting table. I'm not going to go over the whole table as I did last time for the sake of brevity, but I will show you how to produce like a single row. Let's look at the first row. So here we did 1 damage, and then on the second hit we did 1 damage, right? So cumulatively we did 2 damage. In this particular row, we did on the first hit trigger open wounds. Since there's only 2 hits, there's only 1 hit over which we can accrue that damage. So there's only 1 stack of d sub O, right? D sub O being 28, multiplying these, this is the expected cumulative damage between hits in this instance. Now, there will be 0.5 seconds remaining, so we will do 16 damage over that interval of time, resulting in 8 additional damage. Summing these 3 sources, we have our total. That's how we produce each of these like final values in these rows. Okay, now the mean of all of these is 24. So if we inflicted an expected cumulative damage of 24 over a period of 4 seconds, then the analogous expected damage per second inflicted against target X in time tau equal 4 seconds is given by 24 over 4, which is 6. I didn't intend for it to be that clean, but here we are, right? Anyway, it's just kind of convenient, but Here's a question. What was the analogous expected damage inflicted by said character from hits to target X per second in time tau equal 4 seconds? By from hits, I mean, if they inflict 1 to 3 inclusive per hit, what's the average they did there? And care must be taken here. And that's what I mean by care must be taken, because a lot of people actually would get this wrong. I'll explain. So let's look back at our table. If we take the average of the cumulative damage we did in all of these instances, we get 4. Okay? So given that the character inflicted an expected cumulative damage of 4 from hits in time tau equal 4 seconds, it follows the expected cumulative damage per second from hits is actually given by 4 over 4 is 1. This is counterintuitive because I think most people want to take the average and then multiply by the hit rate. We'll get to that in a second, but the important part is now we know. If we had to do 6 in total, and that was 1, then if our equation is correct, we must have that d sub o of 1/2 1.75 bar plus 1 equals 6, when tau is 4 and r sub o is 16. In other words, d sub o of 1/2 1.75 bar must be 5, right? So let's see what happens. We'll plug in these values, evaluate them, and sure enough, we get 5, right? Observe that this plus 1 is 5 plus 1 is indeed 6. So that is as expected. So note that if we had computed the expected damage per hit, right? 1 plus 3 over 2 is 2. And multiplied this by the mean hit rate, which is the reciprocal of the time between hits. So 1 over 1.75, which is 0.571428 repeated. Then we would have overestimated the analogous expected damage inflicted per second within time tau equal 4 seconds, as 5 plus this value is going to be 6.142857 repeated. So this is counterintuitive, but multiplying the average damage per hit by the hit frequency is actually not the most accurate way to determine how much damage you would do over an interval of time tau. And the reason is that not all of those hits have actually gone off yet, right? If we have 0.2 of a hit in that time interval tau, that hasn't yet gone off yet. So really, it only makes sense to multiply in this way if you have an unbounded number of attacks. It's more accurate to do something different, and I'm going to show you what that is. If t bar in the interval 0 exclusive tau inclusive is the mean time between hits in seconds for some character, and mu is the expected damage inflicted by said character to some target x per hit, then a more accurate approximation of the analogous expected damage inflicted by said character from hits to target x per second in time tau is given by mu over tau times the floor of tau over t bar. Thus, to reduce inaccuracies, you should add the analogous expected damage per second inflicted by open wounds against target x in time tau to mu over tau times tau over t bar instead. And in general, if you're trying to calculate a more accurate estimation of your average over an interval of time tau, you should use this as well. When people multiply the expected damage by the hit frequency, this really only makes sense if you're thinking of tau as unbounded. Thus, this is a common mistake by which people, when thinking about the damage they deal over finite periods of time, usually overestimate their damage per second, as well as their cumulative damage delivered in that time. Indeed, as when applying this method, we see that this sum is equal to these values. We know that d sub o of 1/2 1.75 bar is just 5. We just calculated that. The mean damage is just 2. 2/4 simplifies to 1/2, and the floor of 4 divided by 1.75 is just 2. Cancellation of 2's. 5 plus 1 is 6. So this works. Hopefully this also provides more insight into just how accurate this equation is, right? And why tau is a relevant factor even when considering something as trivial as one's damage from hits that they deliver over a period of time. So putting all this together, given an applicable sequence of consecutive hits made against a single target x in time tau, it follows that the analogous expected damage per second inflicted to target x in time tau is given by this formula, where P is the probability to trigger open wounds, and it's greater than 0 and less than or equal to 1. R sub O is the damage per unit time in seconds inflicted by open wounds. T bar is the mean time between hits in seconds, greater than 0, less than or equal to tau. And mu is the expected damage inflicted to target x per hit, right? That's the damage you would calculate from a D2 character damage calculator. And remember, tau is greater than 0 and less than or equal to 8, where 8 is the duration of open wounds.